we're going to continue our video lesson on rates of reaction, and this time we're going to talk about the effects of surface area on those rates of reaction. Now before we start this video lesson, why don't you just pause it after I give you these instructions. Alright, so go to the supermarket and you will buy one of those breast meat, right, that is boneless and skinless. Alright, so you buy that, and usually breast meat comes in two flaps, right, two pieces like that. And so you cut those breast fillet up into two pieces, and then one piece you just leave it as is, and the other piece you will dice it up into small cubes. Now take a big frying pan, and you can add oil if you want, and then you're going to put the fillet piece on one side of the frying pan, and then the cubes, chicken cube fillet, diced chicken meat, breast meat, on the other side of the pan. And then you're going to turn up the fire and you're going to cook it. And make sure that the fire is equally distributed throughout the whole process, okay? And, so your job is to predict which piece of chicken, the fully fillet piece of chicken or the diced pieces of chicken, gets cooked first. So there you go. Go and do that. And come back to me when you're done. Alright. So, have you done the experiment? Great. Now that you've got your results, you should know the answer for this factor and how surface area will affect the rate of reaction. And it's exactly the same. In my situation, I have an imaginary magnesium ribbon put into a container of dilute acid, or HCl. And then in the second container, I'll take the same amount of magnesium ribbon and I cut it into little pieces and put it in another container of diluted acid. And in the final container, I will crush up those magnesium into powder, and then I'll put it into that container. The mass of these three magnesium are the same. Alright, so now let's use collision theory to try and explain what is happening at the atomic level. So in this container where the magnesium pieces are, you will have like the acid moving around, you know, whatever, in random directions. Okay, the acid particles moving around the acidic solution in random directions, and occasionally you have the acid bumping onto the surface of the magnesium ribbon. Now, each little bump particle onto the magnesium ribbon does not usually necessarily equal into a successful collision, but occasionally the bump is hard enough where the hydrochloric acid will react with the magnesium ribbon to form hydrogen gas, and you know that hydrogen gas will kind of bubble its way out of the solution and into the atmosphere. Okay, so but because if you calculate the the surface area here, you will see that it has probably X amount of exposed area. And so the only way that the acid particles get in contact with the magnesium ribbon is only at the surface, leaving the whole chunk of the magnesium as inside here unexposed and not able to react. Okay, so slowly the acidic particles will have to eat off bits of pieces of the magnesium ribbon until it reaches to the center area where the acid particles can come into contact with the magnesium in order for the reaction to occur. Okay, so when we plot that onto our graph, remember this is a probably a mass loss reaction, or you can have it a volume of gas produced. It doesn't really matter. I'll stick with the volumes of gas produced because that's what I've been doing all this while. Okay, the amount of products produced, the gas, hydrogen gas that's released is it's going to be the same no matter whether it's this, or this, because the quantity of hydrochloric acid is all the same. Okay, so it's going to have a graph and it's going to plateau out. All right, over here it's going to plateau out, and there you have your rate of reaction. Right? Why? Because as I've explained, the amount of exposed area for the magnesium ribbon is not very high. But in our second situation, we have little pieces of magnesium ribbon that we put in there. Now I drew in this shape in particular so that you can kind of see that the mass is almost the same, although it doesn't really show that. But because it's little pieces, you can see particles of hydrochloric acid that is able to react in this area of the magnesium pieces. Okay, and so what happens is that because you have more exposed area, more area for hydrochloric acid to react here, what happens is that the rate of reaction will increase because each piece of magnesium has now 4 sites or 8 sites that is exposed in the acidic solution in the acid bath and is able to collide. The acid particles is able to collide with the magnesium pieces to form products. All right, so the rate of reaction should be much higher than the magnesium ribbon, okay, and it will plateau out once the magnesium pieces have all dissolved, not dissolved, reacted with the dilute acid and hydrogen gas is produced. So there you go, that's your other situation. And our final situation is where you have powder, magnesium powder, put it into the acid bath. And so when that happens, you can let lots of particles, of acidic particles that are in direct contact with magnesium, the magnesium powder. So in this instance, the rate of reaction is extremely fast. You see like intense fizzing when you do the reaction. In fact, we have done this reaction in class. Hopefully you guys can recall that. And so the rate of reaction is very high, and it dramatically decreases, and the reaction completes. Okay, so there you go. I drew out the rate of reaction for all these 3 instances. So again, generally speaking, the concept is the same. As you increase surface area, the chances of successful collisions goes up, resulting in a higher rate of reaction. The rate of reaction, again, is always higher at the beginning of the reaction because there are more reactants available. And as the reaction proceeds, the amount of reactants will go down, so will the chance of successful collision until you will get your total amount of products. All right, now as a side note, I would like to point out to you, as part of your learning objective, about the dangers of powder in the industry. Okay? In particular, flour mills, when they grind up those wheat, all those wheat into usable, friendly flour for us to bake cakes and all that, enchiladas. All right, flour mills is especially dangerous because remember, flour is made of wheat, which is basically an organic material, and like most organic material, it combusts when it's exposed to fire. So So what happens is that in flour mills, we have lots of flour dust in the air. And when you pour flour in big bags of goonies and of flour from one place to another, lots of flour dust gets exposed. And if those flour dust is is exposed to a fire source, what is going to happen? You're going to create a big plume of combusted, a highly exothermic and very rapid reaction where the flour will all get burnt when you have a small spark or fire source. To demonstrate this, I think you can guys are old enough to do this safely at home, but not in big quantities. You have maybe a lighter or some fire source that is not high. I would recommend it to do at a kitchen stove. You have a small fire source, and then you take like flour. You have just a little bit, maybe about this much, okay, or like a little finger much. And then what you're gonna do is you're gonna take flour and you're gonna sprinkle it on top of the fire source, and you will see that once the powder gets in contact with the fire will have a small plume like that. So if you're going to try this at home, please be very, very, very careful. In fact, don't really try it unless you have an adult nearby, or you can watch YouTube videos to kind of prove my case. All right. So powders are extremely dangerous. If we get the chance in class, I'll probably do a demonstration on this, but it's going to be pretty dangerous. All right, so we do have to take safety precautions. Don't say that I didn't warn you.